Hello, my name is Mahmood Taghavi and I'm going to present my paper in 2022 International Conference on Ocean, Offshore and Arctic Engineering in Hamburg. The topic of the paper is data-driven digital twin applications towards green ship operations, and this paper was written under the supervision of Professor Perera from UIT, the Arctic University of Norway. Here I'm going to talk about the general order of the sections that I'm going to talk about. The first one is introduction, the second one is materials and methods, and the third and major part is the data analysis. And the last part is the conclusion that we had from this investigation and research. The goal of this research is to find the operating regions of the engine for selected vessel. Because our samples don't have tags and we don't know each point belong to which operating region, we should use an unsupervised learning algorithm which lead us to cluster analysis. For this research, this ship has been selected and the contribution of our work is a digital twin of a marine engine which can be utilized toward green ship operation. The method we use for this research is based on machine learning and statistical analysis. And we know that for every machine learning and statistical approaches, and generally for data-driven approaches, we have to perform a pre-processing to prepare the data to be fed into the algorithm. So the first step of our research was data pre-processing. After preparing the data, we use Gaussian mixture models to find the distributions of different clusters. And in this way, we have some variables that we have to estimate, some parameters that we have to estimate of these distributions. And for that, we use expectation maximization algorithm. After finding these variables, now we have the distributions and their prior probabilities. We can use the clustering based on the result of distributions. And at the end, in each cluster, we can use the singular value decomposition to find the dominant directions and directions which contains the most information in each cluster. Here you can see the general concept and idea of Gaussian mixture model and expectation maximization algorithm, the EM algorithm. In this approach, we have different distributions of the data, and each distribution has its prior probability. Our goal is to find these parameters, which are the mean values and covariance of each distribution and the prior probabilities. An EM algorithm leads us to this iterative scheme for updating and estimating the parameters. The first step for our analysis is the pre-processing step. If we take a look at the left side of the slide, we can see the diagram for three variables. If we take a look at the fuel consumption, we can see that for half of the selected period, the fuel consumption is 0. And from time to time, we have illogical high values for fuel consumption, which have to be removed from the samples because we cannot have a proper analysis if we don't move them. And if we look at the right side of the slide, we can see about 17.5 thousand points have zero main engine power. We want to investigate the operating regions of the engine, so we have to remove the points associated with the time the engine was turned off. And if we remove that, we can have purified data that can be fed into our algorithm. The next step is normalizing the data. Here we can see the covariance matrix for the raw and normalized data. As you can see, the order of the variables and thus the values of the covariance matrix elements differ significantly, so the algorithm is susceptible to putting more focus on the variable with larger values and ignoring the changes in the smaller variables. In order to prevent this from affecting the validity of the estimation, a normalization is necessary for the dataset. In Gaussian mixture models, we have to determine the number of clusters so that the algorithm knows how many clusters it should look for. For that purpose, we use kernel density estimator or KD plots. They're quite similar to Parson density estimators, and we can use them to determine the number of clusters. In the left side, we can see three one-dimensional KD plots that has been plotted for three variables that we have in this research. They're quite similar to histogram, and the denser regions have higher frequency, so the peak for the denser regions is higher. And we define the centers of these denser regions, or our hypothetical clusters, with red lines, and we can find each cluster in these three one-dimensional KD plots. In the right side, we plotted a two-dimensional KDE plot, and we can see that the denser regions are the darker ones, and we can associate them with the cluster centers or the denser regions in the one-dimensional KD plots. At first, the cluster analysis is performed in a two-dimensional feature space with main engine power and fuel consumption as the variables. On the left side, we can see the cluster's final state in the normalized feature space. We can see the cluster centers determined with red points, and the values of the cluster centers are in the right side. We can see the percentages of points belongs to each cluster. We have a major cluster with more than 54% of the data. These numbers shows the amount of time or percentage of the time that sheep operates in each cluster or each operating region. Next, the cluster analysis is performed in a two-dimensional feature space, but this time with main engine power and speed as the variables. We can see the cluster's final state, cluster centers, and again, percentage of data points belong to each cluster. After performing the cluster analysis in two-dimensional feature space, the algorithm is used to find the clusters or operating regions in the three-dimensional space with engine power, fuel consumption, and speed RPM as the variables. In the left side, we can see the final state of the clusters, which has been plotted with different colors, and the cluster centers are shown in the right side. Here we can see the log likelihood function values for different iterations. We can see after about 25-26 iterations the algorithm was converged. The log likelihood function is the logarithm of the likelihood of the parameters, and it is used as a measure of the convergence of the EM algorithm. Again, we can see the percentage of data points belong to each cluster, which shows we have a dominant operating region with more than 55% of the data. After finding clusters or operating regions, we perform the singular value decomposition to find the singular values in each cluster. These vectors have same dimensionality as the feature space and ordered from the largest singular value to the smallest one. So V1 in each cluster has the dominant direction and contains most of the information. In the last section, I'm going to talk about the conclusions of this research. By implementing the Gaussian mixture models and expectation maximization algorithm, four major clusters are captured in the three-dimensional feature space. Increasing the number of features from 2 to 3 improved the separability of the clusters, and the algorithm was converged in fewer steps. Obviously, some clusters are not identifiable in the three-dimensional feature space. For more precise cluster analysis, more operational and navigational variables of the vessel should be considered. There is a dominant operating region of the engine, which contains about 56% of the data points, which means the vessel was operating in that region for more than 56% of the time. In order to find a relationship between the variables, an SVD analysis was performed in each cluster, which resulted in finding the singular vectors of data points in that cluster. Thank you everyone for your patience. I hope you enjoyed my presentation, and for further details and more information, please refer to the paper.